When you stop and think about it, what is our modern world actually built on? It's not really steel or concrete, not anymore. The entire digital universe, I'm talking your phone, the internet, AI, everything, it's all built on a very special kind of material, one that we've learned to control with, well, almost magical precision.
It all kind of starts with a question that's so simple you've probably never even thought to ask it. We all know that the metal wire charges your phone, but the rubber or plastic coating around it can't. I mean, why is that? The answer seems obvious, right? One lets electricity through, one doesn't. But the deep physics behind that simple fact is what has powered our entire technological revolution. So let's dive in. And we're not talking about a small difference here. This chart shows what's called resistivity, basically how much a material fights against the flow of electricity. Over on the far right, you've got conductors like copper. They let electricity flow almost for free. On the far left, you've got insulators like glass, which stop electricity dead in its tracks. And the gap between them, it's just astronomical. We're talking a factor of a billion. But look closer. What's that fascinating little slice right there in the middle? Those are the semiconductors.
To really get what makes that middle group so special, we're going to go on a bit of a journey. We'll start inside the atom, then see how atoms bond together, explore the energy highways they create, meet our Goldilocks material, learn how we can literally hack it, and finally, see how all of that becomes the ultimate on-off switch that powers our entire world.
All right, first stop, we have to shrink way down. We're going deep inside matter to meet the single most important player in this whole story, the electron.
So, every material is made of atoms, right? And atoms are made of just three basic parts. You've got these heavy, positively charged protons and neutral neutrons all clumped together in a tiny, dense core. That's the nucleus. But the real stars of our show, the ones doing all the interesting stuff, are the super light, negatively charged electrons, just zipping around on the outside. Their behavior, it dictates everything.
And for the longest time, we had the atom structure totally wrong. Scientists pictured it as a plum pudding, just a blob of positive charge with electrons stuck in it. It took Ernest Rutherford's famous gold foil experiment to just shatter that idea. When he saw some of his particles bounce straight back, he was just floored. This quote perfectly captures his shock. He just discovered the nucleus and proved the atom is mostly empty space.
But even that new model had a huge problem. According to the physics of the day, an orbiting electron should have been constantly losing energy and spiraling into the nucleus, which would mean all matter should just collapse. The big breakthrough came from a physicist named Niels Bohr. He proposed this radical idea. What if electrons aren't allowed to orbit just anywhere? What if they're stuck in specific fixed energy levels, or shells? They can hang out in one level forever without losing energy. This idea that energy is quantized is the absolute key to everything that comes next.
Okay, so that's a single atom. But of course, materials are made of trillions and trillions of atoms all linked up. So next, let's look at how these atoms hold hands through chemical bonds to build the world we see.
There are really three main ways atoms can bond, and it all boils down to what those outer electrons are doing. In an ionic bond, one atom basically just gives its electron to another. In a covalent bond, they share. But for our story, the really crucial one to start with is the metallic bond.
See, in a metal, the atoms are incredibly generous. Each one donates its outer electrons to this massive shared pool. It's often called a sea of electrons. These electrons don't belong to any one atom anymore. They're totally free to just flow throughout the entire structure. And this electron sea, that's exactly why a copper wire is such a great conductor. It's a ready-made river for an electrical current.
Now, let's pivot to silicon, which is the heart and soul of our semiconductor story. Silicon does things differently. As you can see in this crystal structure, it doesn't create a sea of electrons. No way. Instead, each silicon atom forms these really strong covalent bonds, sharing its 4 outer electrons with 4 of its neighbors. And here's the crucial point. In pure silicon, all the electrons are locked up tight in these bonds. They're not free to move around. That's what makes it act like an insulator.
Okay, so to really grasp the difference between those freewheeling electrons in copper and the locked-up ones in silicon, we need to zoom out a bit. We're going to scale up Bohr's idea of energy levels into a bigger concept called energy bands.
This is a fantastic way to visualize it. For an insulator, on the left, you've got 2 main energy zones. There's the valence band down low, where electrons are happy to be, and a conduction band up high where they would need to go to move freely. But in between is this huge forbidden energy gap. Electrons just can't make that jump. They're stuck. Now look at the conductor on the right. Those two bands overlap. There's no gap at all. It's basically an open superhighway for electrons to cruise on.
So we've got insulators with a huge, impossible gap, and conductors with no gap at all. And that brings us to the hero of our story, the material that is, well, just right.
And this, right here, shows why semiconductors are so incredibly powerful. Look at its energy band diagram. It has a gap, sure, so by default it acts like an insulator. But the gap is small. It's manageable. This is the secret sauce. It means we can give the electrons just a little nudge, maybe with some heat, or much more importantly, with a voltage, and we can get them to leap across that gap into the conduction band. We can control whether it's an insulator or a conductor. We can turn it on and off.
But you know, controlling conductivity with something clumsy like heat isn't very precise. The real world-changing breakthrough came when we figured out how to hack the silicon crystal itself. It's a process called doping. So here's how this hack works. We start with a perfectly pure silicon crystal, where every atom has 4 outer electrons. Then, we intentionally sneak in a tiny impurity. For what's called N-type doping, we add something like arsenic, which has 5 outer electrons. Now, 4 of those electrons form bonds with the silicon neighbors just like normal. But that 5th electron is left over. It's a spare part. It has no bond to hold it down, so it's free to move around and carry a current. We've just created a free negative charge carrier.
And you guessed it, we can do the exact opposite. For p-type doping, we add an impurity like boron, which only has 3 outer electrons. So when it tries to form 4 bonds with its silicon neighbors, one of those bonds is missing an electron. We call this absence a hole, and it behaves just like a positive charge. A nearby electron can jump into the hole, but in doing so, it leaves a new hole behind. So effectively, it's the hole that moves through the crystal. We've just created a positive charge carrier.
Okay, so now we've got 2 custom types of silicon. One with extra electrons, the N-type, and one with extra holes, the P-type. The real magic, though, happens when you stick them right next to each other. This is called a p-n junction. Right at that boundary, the free electrons from the N side see all those empty holes on the P side, and they rush over and fall in, neutralizing each other. This creates a thin layer right at the junction that has no free charges at all. It's called the depletion zone, and it acts like a barrier.
And that little p-n junction, with its built-in electrical barrier, is the fundamental building block for what is arguably the most important invention of the 20th century, the transistor.
So how do we actually make one of these things? Well, a full computer chip is insanely complex, but this gives you the basic idea. You start with a super pure silicon wafer, you grow a layer of silicon dioxide on it, which is basically glass, a great insulator. Then you precisely etch it away, you blast it with ions to create your doped regions, grow another incredibly thin oxide layer, and finally add your metal contacts.
And the end result of that whole process is this beautiful little device, the MOSFET. It stands for Metal Oxide Semiconductor Field Effect Transistor. And really, it's the culmination of everything we've just talked about. It's a tiny, elegant, perfect little switch with no moving parts, and it has 3 connections, a source, a drain, and a gate. And here's the punchline to the whole story. If you apply a small positive voltage to that gate, the electric field it creates just wipes out that depletion zone barrier we talked about, and it lets current flow from the source to the drain. That's on. You remove that voltage, the barrier comes back, and the current stops. That's off. On. Off. 1. 0. This is the physical reality behind all digital logic, and a modern computer chip can do this billions of times every single second.
So just think about the journey we just took. We started with a simple question about a phone charger. We went all the way down into the quantum world of atoms and energy levels. We saw how we could hack a crystal to give it superpowers, and we used that knowledge to build a microscopic switch. By learning to control the flow of tiny little electrons, we built our entire digital civilization. It really makes you wonder, doesn't it? What will be the next material we learn to master, and what world will that let us build?